Hey everyone, I'm going to walk you through this activity here because we didn't have a chance to do it in class. And it involves some teamwork to try to figure out what's going on, and usually I try to help as well. So this is to help you figure out what intermolecular forces are. The first thing is to review the polarity of each of these types of bonds. So you know about the electronegativity difference. So if the atoms are the same, they have the least electronegativity difference, that is 0. And then carbon and hydrogen will be the next one. Nitrogen, hydrogen, oxygen, hydrogen, and fluorine and hydrogen have the greatest electronegativity difference. So for example, the values you may know from the back of the periodic table you have show that fluorine is 4.0 and hydrogen is 2.1. So that's a pretty big difference for the electronegativity. So that means that this is a very polar bond pointed in the fluorine direction. So fluorine grabs most of the electrons in this bond. Whereas hydrogen and hydrogen have the same electronegativity, so their difference is going to be 0. So 2.1 minus 2.1. So that's 0, so this is the most nonpolar. And carbon and hydrogen, hopefully you've been learning that it has a very small difference. So the difference is 0.4. So these are considered nonpolar bonds, and these are considered very polar bonds. All right. Now that we know a little bit about what kind of molecules with these types of bonds tend to be nonpolar, molecules with these types of bonds tend to be very polar. We're going to look at some data now to tie that into physical properties. So for example, these molecules are called alkanes. Sometimes we cover organic functional groups, but if we skip that, alkanes are molecules with carbons and hydrogens only. So if you look at these structures, what that means is there's a carbon here on the end, here in the middle, and here on the end. And then they're connected via the Honk rule or bonding patterns. They've got to have an octet. So hydrogens are implied. So there's hydrogens here to make 4 bonds for carbon, so it fulfills an octet. Carbon wants 4 bonds here, so there's 2 hydrogens, and there's 3 hydrogens here. So you can see the difference between propane and butane then is that butane has 4 carbons instead of 3. Looking at their properties then, the weight of this molecule is going to be different from the weight of this molecule. So those are in atomic mass units. There's the dipole that can be measured. So we've been predicting dipoles just based on electronegativity difference. But the overall dipole of the whole molecule can be measured and is shown here. So this is pretty much 0. So that tells us about polarity. Dipoles tell us about polarity. So in this case, these molecules are not very polar then because their dipoles are 0 Debye units. And boiling point tells us the temperature at which this sample of molecules will boil. So this one boils at 0 degrees C, this one boils at negative 42. And this is solubility, which means how many grams per 100 milliliters of water it will dissolve in water. So solubility in water, how well does it dissolve in water? Okay, if you look, there's some other functional groups as well. So there's alcohols, which all have this carbon-hydrogen chain, but with an OH on the end. So oxygen-hydrogen bonds on the end. And if you look back here, those are very polar, right? So let's see if that changes anything. The weight is the weight, so that's fine. But all of a sudden, look at the polarity jumped up to 1.7. The boiling points have jumped up as well, and the water solubility has jumped up as well. So that's sort of the idea here, is looking at these data and comparing the molecules, and then looking at what happens with their properties as well. Same with ethers. We have carbon chains, but with oxygen in the middle. So just a little note here. So for diethyl ether, we've got CH3s on the end. In order for carbon to have an octet, it's got to have 3 hydrogens. And then instead of putting H's on the O likes to have 2 bonds, so it's got to have 2 lone pairs. Same thing here, but with an extra carbon. Carbon, carbon, oxygen, carbon, carbon. And are these ethers, are they as polar as these alcohols? If you look at the dipoles, they're a little bit smaller, so I would say they're not as polar, and the boiling points are much lower. And the water solubility is still high. So mainly it affects boiling point and the polarity, the dipole values here. So you're learning 3 different functional groups: alkanes, alcohols, and ethers, structurally how they're different from each other, and how they affect these physical properties. And that's all going to have to do with how attracted these molecules are to themselves. So for example, one ethanol molecule, how is it attracted to another ethanol molecule? Because these samples have lots of molecules in them. Let's go into that a little bit more. So according to the dipole moments, which functional group is most polar? Well, we talked about how the dipoles here, the Debye units, they're greatest for the alcohols. And the more polar a compound is, it looks like their boiling point is also quite high. So it's going to result in a higher boiling point, the higher the polarity is. For each of these molecules indicate the boiling point how it changes with molecular weight. Well, what they mean by that is if I take propane and I look at its boiling point or its molecular weight, what happens when this chain grows longer and the molecular weight goes up? The boiling point goes up. So it went from negative 42 to 0 degrees Celsius, which means it's increasing in boiling point. Let's do the same here. As the molecular weight increases, as this molecule gets larger and heavier, the boiling point also gets larger. And same thing here, 46 to 72, it's getting larger. Here, negative 23 to 35, that's getting larger. So for all of these, there's the same trend that as the molecular weight gets higher, the boiling point gets higher as well. So that's an important thing to note, that there's a relationship or correlation here, could be a relationship. Intermolecular forces are the attractions molecules have for one another. So just to briefly review, if I have a molecule here and it's bonded to things, like a carbon bonded to 4 hydrogens, for example, the bonds that hold this molecule together, these bonds are called covalent bonds. But if I have another molecule, as normally don't work with one molecule at a time, but if you have a sample of molecules, it's many, billions of molecules, more than that. So you're bound to have multiple molecules around, and the intermolecular forces, IMFs, those IMFs are the forces between those molecules, so the attractions that they form for each other. Because inter means between, like interstate highways between states. So inter, between, and then molecule forces between molecules. So the stronger these forces are, how that affect the boiling point? Well, when we talk about phase changes like boiling something, we go from, let's say, a liquid where the molecules are closer together to a gas where the molecules are farther apart. So I'll just draw that these molecules are now farther apart from each other, meaning that they're in the gas phase, if this was a liquid to start with. So what that means is that these forces between the molecules, these IMFs, need to break in order for the molecule to change its phase. So if these forces are stronger, then that means it needs more energy in order to break that stronger intermolecular force. So that more energy that you're going to need, that higher energy, is going to result in a higher boiling point. So if you take a look up here, for example, so it takes only 78 degrees to break 2 ethanol molecules, or to break a sample of ethanol molecules from each other. So not to break the covalent bonds, but to separate those molecules. Well, for this molecule, it takes 82 degrees. And so for this one, it takes 118. So that's sort of telling me that it's going to take more energy to separate butanol from each other than ethanol from each other. So that means butanol might form stronger intermolecular forces. All right, find one molecule from each functional group and roughly the same molecular weight, because molecular weight is a variable that affects the boiling point. They want us to do a control. So we're going to find 2 molecules different from each functional group with roughly the same weight and rank them in order from high to low boiling point. So what they mean to do here is find molecules with similar boiling point, but from each category. So I see 46, 40, 44, 46, and 46. So we can take that, for example. Okay, and we're going to look at propane and look at its boiling point. So it's got negative 42, 78, and negative 23. So what that tells me is I'm controlling for molecular weight, because we know the higher the molecular weight, the higher the boiling point. So I don't want to compare apples and oranges. I want to make sure I'm comparing apples to apples. And so with the same molecular weight, but for these three different functional groups, the boiling point is drastically different. So that tells me there's something about these molecules that is affecting that boiling point, that is irrespective of their molecular weight. So yeah, so let's see. It's telling me that the alcohols tend to have a higher boiling point than the ethers, which have a higher boiling point than the alkanes. So rather than write that down, I'm going to jump to the next question. Based on your answer above, which functional group appears to have the strongest intermolecular forces? Well, it's the one with the highest boiling point. It's going to take more energy to separate molecules of ethanol than the molecules of the others. So I'm going to say alcohols there. And the lowest boiling point tells us about the weakest intermolecular forces. So it doesn't take as much energy for the alkanes to be broken apart or separated from each other. And when I say broken apart, I don't mean the covalent bonds are breaking. Again, I just mean the molecules are separating from each other. It'll take even more energy if you want the covalent bonds to break. So the covalent bonds are stronger than all these intermolecular forces. Circle the types of bonds that you see. Well, we went through what those structures mean. These are the skeletal forms of these structures. So I know alkanes have C-C bonds and CH bonds. Alcohols have the same, but also an OH bond and an OC bond right here, because that's a C right there. And then we also have OC bonds and CH bonds in these ethers. So just to go back, you can go back and forth and refer to them, but alcohols have all of these types, ethers have these types. So notice that when we categorize polar and nonpolar, we've got our nonpolar types of bonds here, and we have our polar types of bonds on the other side. So here's my nonpolar, and then here's my polar. And then I have very polar even right here. So those are the ones that are going to hydrogen bond. These are going to be your dipole-dipole types of interactions, and these are going to be only your dispersion forces. Now all of these will experience dispersion as well, but dispersion only here. So that makes it, that sort of gets to the essence of what this activity is for, is to point out that, oh, you know, alcohols, now that I know what those are, they have OH bonds, they're very polar, they can hydrogen bond with each other. What type of bond seems to account for the most polar functional group? So because alcohols are the most polar, let's take a look. Well, these are dispersion forces that are present in the other molecules. These are present in ethers as well, but these are present only in the alcohols. And these are the reason why alcohols are so polar, appear to be the reason. So, so it appears that the polar functional groups are more water soluble. Let me show you where that is at. We talked about that briefly up here. This is water solubility up here, so definitely higher for your alcohols and ethers, which happen to also be more polar. So these are all related concepts. High boiling point, high water solubility, and polarity are all related, as well as molecular weight. As molecular weight increases, water solubility, let's take a look at that. Is there a relationship there? This is getting higher, but the water solubility is very high, and then only 6.3. So it appears that the longer this chain gets, the more nonpolar we're getting, not because of the dipole, but because the water solubility indicates that this carbon chain is growing, and even though there's a strong dipole from the OH bond, it's not enough to keep this whole molecule dissolved in water. And the reason for that is this carbon chain is undergoing dispersion forces with each other. and dispersion forces only for these guys, but for this part it's hydrogen bonding to water. But water doesn't form strong attractions to this part that's nonpolar. So that is the reason why the water solubility is decreasing, is because this molecule overall is growing its nonpolar region, this carbon chain here. So does water solubility change? Yes, it does. And it decreases as the carbon chain in particular increases. The dipoles for water, you should all know this by now. Oxygen is more electronegative than hydrogen, so it's got more of the electron cloud over it. Now the magnetic water molecules are just these little magnets that are shaped like water, and they're just to illustrate those attractions in the dipole. So here's water, oxygen, and 2 hydrogens, and it's got this partial negative end right here for the oxygen. And the magnetic water molecules just attract each other oppositely. So you've got this hydrogen, and they will just come together in this region right here. Okay. By now you guys hopefully know this is called a hydrogen bond right there that attracts these 2 water molecules to each other. So we're going to draw that down here in this box. You'll draw 2 water molecules, and I'll use the proper colors. We usually use red for oxygen, and we use white for hydrogen. Okay, so here's my 2 magnetic water molecules, and they're not really magnetic. The magnetic part of the water molecules in the toys that we have, magnets that we have in class, they're just to represent the opposite charges and how they attract. So they're not. It's not that water is magnetic. They're magnets because it's just to demonstrate the pull that they have together. I hope that makes sense. Here's the partial positive. Here's the partial negative on oxygen and the partial positive on hydrogen. And then these 2 regions attract, not the oxygen and the oxygen, but the hydrogen and the oxygen attract each other. And that's what forms a hydrogen bond. And then all of these guys in here, those are all covalent bonds. What holds the molecules together are the covalent bonds. So the OH bonds right here are covalent. Attractive forces, that's this H bond. When you break the 2 magnets apart, you'll see that you're breaking what is represented by the hydrogen bond, what we're representing as the hydrogen bond. So when you evaporate water, you're not breaking these bonds apart, you're just you're separating these molecules. So that's where we have only intermolecular forces breaking. It takes a lot more energy, like I said, to break these bonds as well, and then you would have a chemical reaction, which we'll learn about later. The attraction between 2 molecules is called hydrogen bonding. They're not covalent bonds, they're much weaker than covalent bonds and more easily broken. And that's what's happening when you're boiling things or when you're melting things. You're breaking those hydrogen bonds or intermolecular forces. They're usually shown by dotted lines, and only one of these is a correct interaction. And to get there, all you have to do is know which bonds are very polar, and what are the dipoles, and what are those partial positive and negative charges. So for example, in this molecule, this is methanol, CH3OH, it's alcohol. We know the OH bond is pretty polar, so I'm going to put partial positive there. But this part, CH, that's not polar, so I'm not going to put partial positive here. But even if I did, they wouldn't attract each other. But the point is that this is not polar. If we look over here, this part is partial positive. This part is partial negative because they're part of the OH bond, which is very polar. It's because this H is attached to an O that makes it partial positive, as this is partial negative. That partial positive negative are opposite and they attract each other. So I would say that is definitely a correct hydrogen bonding interaction. And then next, here, do you guys see what's wrong here? It's the same thing as what we had in the first case. So this is definitely partial negative, but this is nonpolar over here. Because carbon and hydrogen have similar electronegativities, I can't say this is partial positive. So it's not going to form very strongly there. So it'll probably just be a dispersion force, if anything. And then over here, this is partial positive because this is partial negative. So I'm going to write that in. And this is also polar bond, partial positive. But positive and positive repel each other. So they would not align in this fashion. So there's something wrong with all of these, except for this one. Which of these would exhibit hydrogen bonding then? If I had another molecule like it, for example, when I ask which of these samples would exhibit hydrogen bonding, I don't mean the molecule, within its molecule, because those are covalent bonds. I mean, if I had another molecule like it, would it form any interactions between themselves? And if so, what type of interactions would there be? So the first thing is, you might want to see, is this considered very polar or just polar? What we consider very polar are these ones from the beginning right here. These have very high electronegativity difference because hydrogen is very low and these are very high. Anything else is not considered strong enough polarity to have hydrogen bonding. So because there's no sulfur hydrogen listed there, because there's no sulfur hydrogen listed there, this is just going to be polar. And so these will have dipole-dipole interactions, which are for just polar molecules. For this one, we do have fluorine, but it's not connected to hydrogen. It's connected to a carbon. So the electronegativity difference isn't going to be high enough. So because carbon has a little bit higher electronegativity than hydrogen, and this one's higher, so the difference is going to be different than if it was hydrogen and fluorine. So, but this one is still polar because there's the dipole. So if I had another molecule like this, it would potentially form dipole-dipole as well, like that. Now technically we don't use these dotted lines for dipole-dipole, but I'm just showing them as an illustration of attractive forces between molecules in general. But usually we reserve these for hydrogen bonding. The next part is this. This molecule has CH bonds, which are nonpolar, but it also has CN bonds, which are polar, and then NH bonds, which are very polar. So this part can hydrogen bond. And if you're asked to show the hydrogen bond, maybe you would draw another molecule like this and show how the regions of this molecule interact with each other, because these hydrogens are partially positive and this nitrogen is partially negative. So the hydrogen bond would be like this. So this one can exhibit hydrogen bonding, and I've drawn how they exhibit that hydrogen bonding. What do you think about this last one here? Hydrogen bonding or no? Well, exactly like this one, NH bonds and OH bonds are polar. So this is partial positive, and the oxygen is partial negative, and it's very polar here. So I can draw another hydrogen bonding interaction like this. And I'm just going to draw CH3 instead of drawing it out. And this is partially positive, and this is partially negative. And because these are very polar, NH, OH, and HF, very polar, I'm going to draw hydrogen bonding there. So this also can hydrogen bond. And you don't have to go through the whole thing and draw it unless they ask you to. You can usually tell just by looking at the types of bonds that are in these molecules. I can tell by looking at this NH bond that, oh, that is a place where I can do some hydrogen bonding. Or over here, OH bonds, I can tell, oh, that's a very polar, it's going to be able to hydrogen bond over here. And over here, this is CH, I know that's not HF, so that's not strong enough, and SH is not strong enough to form hydrogen bonds. So they're still polar though, so I just call them dipole-dipole.